Today we discuss the most basic building block of mathematics. It's called the set. In mathematics, engineering, and physics, complex designs are usually a collection of simple modular objects. Think of engineers. They build amazing gadgets like self-driving cars, but those gadgets are really just collections of smaller, more well-understood components connected together. To understand complex, we must understand simple. And that's why we start with sets, the most basic and simple object in mathematics. A set is simply a collection of objects. That is the traditional definition found in all mathematical textbooks. These objects in a set can be tangible, like marbles in your hand, or intangible, like numbers or colors. Similar to how a computer scientist encapsulates data in structs and classes, sets provide encapsulation tools for mathematics. Encapsulating objects into a set, then giving it a name, is extremely useful. The objects can be referenced by the set's name in a very efficient manner, similar to the way a computer scientist will collect a lot of objects up into a class and then use the class's name to reference the objects. The idea is very general. Almost anything you can imagine can be grouped into a set, including other sets. Sets have two important properties. First, order does not matter in a set. A set containing the numbers 1, 2, 3 is the same as the set containing the numbers 3, 2, 1. Sets do not allow duplicates. With respect to mathematics, the term duplicate can be misleading. Specifically, the idea of duplicates can be a bit deep. Mathematicians utilize special words to describe the level at which items are considered duplicates. In this particular case, we'll stick to the words equal or equivalent. So let's consider pizza. One pizza may be cut into 2 slices and the other cut into 6 slices. Having 1 slice of the first pizza and 3 slices of the other pizza essentially represents the same amount of pizza. But the scenarios are not identical. In this case, we should use the word equivalent rather than equal. As another example, Papa John's and Pizza Hut use different ingredients. Their pizzas are different. But if our definition of equivalence is simply, is it pizza, then they are equivalent up to that definition. This attempts to illustrate the difference between exactly equal and being equivalent under a definition. If all this sounds a little confusing, that is perfectly normal. We can avoid the confusion and stick to basics for this lecture. To provide a very simple example, consider a set that contains the number 3. If I add the number 3 to the set again and then check which elements are in the set, I would find that there's only one 3 in the set. Mathematics is considered a universal language and very different from your spoken language in that it uses symbols primarily. Two mathematicians that speak two different languages can communicate quite efficiently using mathematical symbols and expressions. Let's go ahead and introduce some basic mathematical symbols. We have a special symbol to indicate whether an object is a member of a set. To be clear, objects in a set are referred to as elements. You should get in the habit of using the word objects until membership has been established. Once it's been determined that an object is a member of a set, that's when we can start referring to it as an element. Now notice that the expression in the blue box on my slide. It indicates that X is an element of set A. Now notice the red box. This is an expression that denotes X is not an element of set A. The two expressions look very similar and only differ by a slash through the membership symbol. It is very common in mathematics to simply append the word not when a slash is present. There are 3 primary ways to represent sets. We have sentence form, which we probably want to avoid when possible, roster form, which is very straightforward and simple, and set builder form, which requires a bit of mathematical maturity. Each will have its appropriate use case, and in many instances, sets can be represented by multiple representations. Some will be more appropriate than others. Mathematicians can even convert one representation to another. Each form has its advantages and disadvantages. So to get started, let's consider sentence form. One way to describe a set is just describe it using sentences. For example, let set A be the set of numbers 1 through 10, but this introduces quite a bit of ambiguity. Notice that I said between 1 and 10. Does that mean 1 and 10 are included? Could a person choose the numbers 16 over 3 or 2 pi, since both of those are greater than 1 or less than 10? Is it possible that I really meant whole numbers? So sentence form is flexible, but to be precise in sentence form, it tends to make things very wordy and cumbersome. So now let's consider roster form. Much more straightforward and much easier, and much more precise. This is similar to a class roster, just like a list of the elements. For example, the set of numbers 1 to 10 can be written explicitly as I've got it on my slide. Each number is an element of the set if it's seen to be in the list. If elements of a set can be arranged in a nice, neat, and easily identified pattern, then we can incorporate dots called ellipses to imply ranges. We can also write infinite sets using roster form by appealing to sequential patterns. Notice that we always use braces. We do not use parentheses or brackets because those imply something different in mathematics and in computer science. I did introduce two new terms, finite and infinite. We will tackle these labels in more detail in another lecture, but for now, a finite set simply means that there are a limited number of elements in the set. An infinite set means that there is no limit to the number of elements in the set. Now finally, let's talk about set builder form. This is kind of the fancy approach and requires a bit of mathematical maturity. Think of set builder form as a recipe. A recipe contains a list of ingredients and directions on how to use and combine the ingredients. This method allows us to create complex sets using simple sets. Notice how this is getting to the point I was making earlier about complex objects, being composed of modular, simple objects. Set builder form requires some practice to master. Set builder form is often used when elements are defined by their construction. So let's take a moment and let's consider an example that we will eventually convert to set builder form. Suppose I want to create a set of all positive fractions where the numerators and denominators are positive whole numbers. We can start with all the fractions where 1 is the numerator and then increment through the denominators. Then we consider all the fractions where 2 is the numerator and then again iterate through all the denominators. Now imagine we continue this pattern where we're iterating over whole numbers for the numerators. Notice how I'm describing this set using sentence form. It is very likely hard to follow the construction of this set with words only. So let me take a moment to demonstrate what I'm talking about by using my notebook. Okay, so we were discussing the set of numbers. We'll call it T. We will label this set T. All the set of numbers who are fractions of the whole positive whole numbers. So what I could say is, to give a construction based on what I was trying to imply earlier, T is equal to this set. Well, we'll start out with where all the 1's are numerators. So we have 1 over 1, 1 over 2. Notice how I'm incrementing through the denominators where the numerator does not change. And then dot, 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 implying that the denominators will continue on to infinity. Now we'll continue with the fractions where 2 is in the numerator. So we have 2 over 1, 2 over 2, 2 over 3, 2 over 4, and then dot, dot, dot. Notice that this row is all the fractions where we have a 2 in the numerator and we increment through the denominators. Now we'll go to the 3. So we have 3 over 1. And then we have 3 over 2. And then we have 3 over 3. And then we'll have 3 over 4. And then we'll continue on with this one. Now notice that horizontally the numerators are staying stationary and the denominators are being incremented. Now notice that as we go vertically, the numerators are incrementing. So maybe what I'll do is I'll put perhaps dot, dot, dot this way and then close the set. So you can see now that we have T is effectively written in roster form, but it's not super concise. I mean, truthfully, this is roster form. This is valid roster form, and it is understandable, but it is not necessarily concise. So this is what I was getting at with the construction about how I was trying to describe this set using sentences, but it was becoming very wordy and it was very difficult. So roster form kind of comes to the rescue somewhat. Okay. Now this set, if you can see, I've kind of given a more abbreviated representation, can easily be represented in set builder form in a very nice, concise fashion. More to the point, a much more mature and typical mathematical fashion. So what I'm going to do is, if you notice at the top of my slide here, that is the set builder form. So I'm going to go back to my notebook and I'm going to try to explain this set builder form to everyone. Okay, so this is the set in roster form. So what I'm going to say is now, let's set T, and by the way, when I give it the same name, I'm saying that this set, which is in roster form, will now be written in set builder form. So the way we read this, and so what I'm going to do is I'm going to basically write it out, and I'm going to say out loud, because remember, mathematics is a language, correct? Mathematics is a language that's full of symbols. And what you do is you convert those symbols to your spoken language, but two mathematicians will understand this representation in their own spoken language, but they can read it in a mathematical format. So we have T, the way I read this, let T be the set of numbers having the form A over B such that A and B are elements of the set 1, 2, 3, dot, dot, dot. Close that set, it's an infinite set in roster form, and then we close it. So if you guys remember, set builder form is kind of like a way that we can construct more complicated or sets with more complicated elements using more simple sets. And this is getting to the point that I was making earlier. We use set builder form to take simple objects and extend them to be more complex objects. Now, if you guys remember, and I'll change my color to make sure that we follow along okay, remember what I said. A set builder notation could be resembled like a recipe. I haven't said that quite yet, but I will. I got a little ahead of myself. So this is very much like a recipe. A recipe includes a list of ingredients. And then we have a direction on how to use those ingredients. So we'll call this the directions. Now notice what the ingredients are. The ingredients are the set of numbers 1, 2, 3, all the way up to infinity, but you guys see the pattern. Notice that the numerators and denominators for these fractions that are elements of this set T, they come from this set 1, 2, 3, dot, dot, dot. Okay, but that's just where the ingredients come from. That's just what A and B can come from. A is the numerator, B is the denominator. Notice that we have that. Over here as our direction. So we have in the directions of how to use the ingredients, we're constructing a fraction. So on the left side of the bar, that determines how the ingredients will be used. On the right side of the bar, that's effectively the ingredients. And so with all this put together, we effectively have what I have labeled as a recipe. Okay? So set builder form is like a recipe. You have ingredients and then you have directions. So here you see this entire format is effectively a concise representation for this easy to understand roster form, but not very concise. And both of these are much, much better than trying to describe this construction using sentences as I was using before. Okay, so now I am willing to offer a little bit of advice for you guys that are looking for new ways to become cool and happening people, or you want to impress your friends. If you're looking for tips to impress your friends at the next tailgate party, let's say, you can demonstrate how to represent the set of even numbers and odd numbers using set builder form. So if you feel like that would be some good advice, please let me take a moment to show you how we can do that. I'm going to represent the even and odd numbers using set builder form. So let me go back to my notebook for just a moment and I'll demonstrate this. Okay, so let's be clear. Let's first talk about what the even numbers actually are. So we'll say, let me go back to this color, shows up just a hair better. So we have the even numbers. Oops, I need to turn that off. My tab was trying to help me with the math expression. Sorry about that. So we have the set of even numbers, which are maybe 0, 2, 4. Let's stick with the positive. 0, 2, 4, 6, 8, and then dot, dot, dot. I believe everyone here from when we were little, we understand where this set's coming from, right? So let's suppose that I want to represent this set in set builder notation. So clearly, let's be honest, roster form for this case would be perfectly fine, and it makes perfect sense, and it's very easy to understand, and everybody would see the pattern. But for our purposes, we were trying to make you very cool at the next tailgate party, so I'm going to show you how you can do this in set builder form. I want you guys to look at each one of these numbers. Each one of these numbers has a very specific form in that, notice that I could write 2 times 0, and then I could do 2 times 1, and then 2 times 2, and then this will be 2 times 3, and this will be 2 times 4. And you may say, well, okay, that's neat. Why are you saying this? Well, because what is the definition of an even number? It's a multiple of 2. So I'm using that definition to actually create my set builder form, because that's what set builder form does. It uses the definition of an element to construct them inside the set. Okay, so here's what I want you guys to notice, and I'll draw this maybe in red. Notice that this value doesn't change. I keep multiplying by 2 at each step. But take a look at this value. I'm incrementing over those values 0, 1, 2, 3, 4. So if you want to see how we can write this in set builder notation, I will say E is equal to the set of numbers having the form 2 times K such that K is an element of the set 0, 1, 2, 3, ... And this is kind of a classical set builder notation type framework, if you know what I mean. Okay, so this is effectively showing how you can convert roster form to set builder form for elements that can be constructed effectively. So I want you guys to take a peek. I'll write this. Notice that this 2 is coming from here. Each one of these 2's is coming from here. And notice where the greens are coming from. The greens are effectively iterating over this K. Why? Because we have 0, 1, 2, 3, 4. Notice that K increments over the values 0, 1, 2, 3, 4. So effectively you iterate K as the ingredients. You're getting them from the set 0, 1, 2, 3, ... And then on the left side of the bar, you're writing 2 times those values. And then what you have is you have the set of even numbers that were originally provided in roster form, and now we have converted them into set builder form. Excellent. Okay, so I think I made the promise that I would show you how to represent both even and odd numbers, correct? So what I'm going to do now is I'm actually going to represent the odd numbers in set builder form and then show you how you can convert set builder form into roster form. So let's let O, let's go back to this color, shows up just a little bit. I like to use colors to annotate things. Sorry about that, I jumped ahead. I like to use colors to animate, to illustrate things, and just a simple white on black text to just write. So let's let our set of odd numbers be this. 2K, 2 times K plus 1, such that K is coming from the set 0, 1, 2, 3, ... And then we close it off. So this is the set of odd numbers represented in set builder notation. Remember, we have our ingredients over here on the right side of the bar, and then we have our directions on how to use those ingredients on the left side of the bar. So I'm going to read this again. Let set O be the set of elements having the form 2K plus 1 such that K is an element of the set 0, 1, 2, 3, ... Okay, let's see. That means that we can rewrite O in roster form by using the ingredients and the directions. So watch and see what I do here. So we're going to do 2 times 0 plus 1, comma, 2 times 1 plus 1, comma, 2 times 2 plus 1, comma, 2 times 3 plus 1, comma, ... Okay, so let's make sure that we digest exactly all that's happening here. I'll use my annotation here. So notice that we have the 2 that's present everywhere. Notice that that 2 is here, 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 and here. Notice that we have this incrementer K. And where does K come from? It's iterating over those ingredients on the right-hand side of the set builder notation. So we have 0, notice that's here. We have a 1, 1, 2, 2, 3, 3. Notice that they're coming from the set of elements from the ingredient side. And then we finally have this plus 1. Notice that we have plus 1, plus 1, plus 1, plus 1, plus 1. So all I need to do now is just convert these things and do a little simple arithmetic on these individual elements. So the set of odd numbers looks like this. 2 times 0 is 0 plus 1. 2 times 1 is 2 plus 1. 4 plus 1. 6 plus 1. And then ... And then if we go through and simplify just one more time, we have 1, 3, 5, 7, ... Now, if you guys want to hear something that's kind of neat, so this, well, before we get to that, notice that this is effectively set builder form here, and we have converted it into roster form here. So we have set builder form here, and then we have roster form down here. So we went both ways. We went from roster form to set builder form with the even numbers. We went from set builder form to roster form with the odd numbers. So again, remember I advertised this as saying, if you're looking for a way to be cool for all your friends that you're going to meet at the parties and whatever else, this would be my suggestion. Pull this out on a little board that you can take with you, a little marker board, and say, hey guys, you guys want to do some conversion between sets, set builder form and roster form? It'll be a blast. You'll immediately become one of the coolest people that everyone knows, right? Okay. So we have all these things under our belt. So let's now wrap up this lecture because I pretty much showed what I want you to learn. The three ways to represent a set, the notation. So let's wrap this lecture up. All right. In this lecture, we learned that sets are the foundation of mathematics. We saw their properties, different forms of representation, and how notation makes them precise. The topic may feel simple, but it is essential, and clumsiness can kind of sneak in, as we'll see in future lectures. Science and engineering demand precision. Small misunderstandings can lead to major failures, servers that cannot communicate, or bridges that are weaker than expected. By learning sets carefully, we build the habits of precision that science requires to function. So, thank you for watching this lecture. I encourage you to leave helpful comments. Those will help me as I create other lecture videos. If you find this lecture helpful, then please provide a positive thumbs up. I look forward to hearing from all of you. Thank you for watching and have a great day.